Combining uncertainties. Often the quantity we want to find will depend on two or more measurements. For example, if calculating the speed of an object from the distance travelled and the time taken, there will be uncertainties in both of these measurements. We could have used a light gauge with a blanking card of 10 centimetres, measured with a metre rule and therefore to an accuracy of plus or minus 1 millimetre, and we could have stop clock times given below. The stop clock gives an uncertainty of plus or minus 0.01 seconds, but half the spread is given by our largest value of 0.28 seconds minus our smallest value of 0.25 seconds divided by 2. This is 0.02 seconds. The mean will be 0.26 seconds, so we'll use our largest uncertainty of the 0.02 seconds being larger than the stop clock uncertainty of 0.01 second and quote 0.26 plus or minus 0.02 seconds. To find the uncertainty in the speed, we could calculate the maximum speed using the longest possible distance of 0.101 meters with the shortest possible time of 0.24 seconds, and this gives a speed of 0.42 meters per second. We could then calculate the minimum speed using the shortest possible distance of 0.099 meters and the longest possible time of 0.28 seconds, and this gives a speed of 0.35 meters per second. The mean is the largest plus the smallest over 2, giving 0.39 meters per second. So we could quote 0.39 plus or minus 0.04, which includes our lowest figure of 0.35 and overtakes our higher figure of 0.42. However, it is easier and often more useful to use percentage uncertainties. Percentage uncertainty is calculated from the actual uncertainty divided by the measurement and multiplied by 100 to give a percentage. So for the length measurement of 0.100 plus or minus 0.001 meters, the percentage uncertainty is our uncertainty of 0.001 meters over our measurement of 0.100 meters, times by 100 gives a figure of plus or minus 1%. For the time measurement of 0.26 plus or minus 0.02 seconds, the percentage uncertainty is the 0.02 seconds uncertainty over the measurement of 0.26 seconds times 100, or plus or minus 8%. To combine percentage uncertainties, we simply add them, so the speed will be to an uncertainty of 1% plus 8%, giving plus or minus 9%. We can therefore quote the speed as given by distance over time, which is 0.100 meters over 0.26 seconds, a speed of 0.38 meters per second, with an uncertainty of 9% of 0.38 meters per second, which is plus or minus 0.03 meters per second, giving a final figure of speed is equal to 0.38 plus or minus 0.3 meters per second. Percentage uncertainties always add. So for example, the percentage uncertainty in a value x in the following situations will be given as shown. Where x is equal to a times b, the percentage uncertainty in x will be given by the percentage uncertainty in a plus the percentage uncertainty in b. Where x is equal to a over b, again the percentage uncertainty in x is given by the percentage uncertainty in a plus the percentage uncertainty in b. If x is equal to a squared, well, this is just another way of writing x is equal to a multiplied by a. So the percentage uncertainty in x is equal to the percentage uncertainty in a plus the percentage uncertainty in a, or alternatively 2 times the percentage uncertainty in a. If x is equal to a plus b, then again the percentage uncertainty in x is given by the percentage uncertainty in a plus the percentage uncertainty in b. And finally, if x is equal to a minus b, yet again the percentage uncertainty in x will be given by the percentage uncertainty in a plus the percentage uncertainty in b. Another useful feature of percentage uncertainties is they tell us where to start improving our experiment. In the example used earlier, the length measurement had an uncertainty of just plus or minus 1%, and the time measurement an uncertainty of plus or minus 8%. Clearly, we'd be better off trying to improve on the timing accuracy before thinking about how to improve the length measurement.